So this video will just be showing you how to do a few of the problems concerning isomorphisms on page 138. Number 4, show that U8 is not isomorphic to U10. What you usually would do is check the properties that we have and find one that does not hold. For example, U8 and U10, I would look at the orders of the elements. In U8, if you look at the orders of the elements, you'll see that 3 squared is 1 mod 8, 5 squared is 1, 7 squared is 1. So we have here 3 elements of order 2. But over here, checking, we find that U10 is actually generated by 3. It's cyclic. A cyclic group of order 4 has 2 elements of order 4, and it has 1 element of order 2. So we know that U8 has 3 elements of order 2 and U10 has 1. Therefore, they cannot be isomorphic. The reason is property 5 in one of the 2 sets of properties tells us that the order of A is equal to the order of phi of A under an isomorphism. So that can't be true if we have 3 elements of order 2 in one group and 1 element of order 2 in the other. In problem 5, we want to show that S4 is not isomorphic to D12. They both are groups of 24 elements, and they're both not abelian. So we'd have to, again, think of orders of elements in the 2 groups. In D4, we have elements of order 2 and 4. In S4, though, we have, let's see, we have 4 cycles. In S4, we have 4 cycles. We have 3 cycles. We have 2 cycles, and we have 2 cycles. Well, the one I'd like to focus on here is the 3 cycles. Those are of order 3, and we have several of them of order 3, all the 3 cycles in S4. We don't really have to count them, but just so you know what I mean by 3 cycle, elements like 1, 2, 4, 4, 1, 4, 1, 3, 1, 2, 3. Those are 3 cycles, and they all have order 3. So my answer to this question would be, in S4, there are elements of order 3. In D4, there are no elements of order 3. Therefore, S4 is not isomorphic to D4. Now this problem, before we do it, let's think about it. This one isn't so obvious how you could solve it. H is the set of permutations in S5 that fix 1. For example, in H, we would have the permutation fixes 1, so maybe 2, 3, 4. That's a permutation that does not move 1. And over here in K, the permutations that don't move 2, we would have 1, 3, 4. So what I'd like to find is a mapping that would map this permutation to that permutation. In other words, if you saw a 2, it would be replaced by a 1. So let's see. Let's take 2, 3, 4 and permute it by the one that switches 1 and 2. Right, if we called this alpha, that's alpha inverse. A 2-cycle is its own inverse. So let's see, if we permute by that, let's see what we get. I'll put 1 down. If 1 goes to 2, 2 goes to 3, and 3 stays the same. Now 3 goes to 4. Now from 4 goes to 2, but alpha takes 2 back to 1, so we close. Let's take a permutation, another one, and just try it again. One that fixes 1. Let's say 5, 3, 4, 2 fixes 1. Again, let's multiply it. Let's conjugate using alpha is 1, 2. So this is just checking out to see if this is a mapping we might like to use. So let's see, we get 1, 1 goes to 2, 2 goes to 5. And then 5 goes to 3, 3 goes to 4, and 4 goes to 2, but alpha takes 2 back to 1. So we see again that it has taken this permutation, 5, 3, 4, 2, and changed it into 5, 3, 4, 1. I mean, the 1 is in the first. This is the same thing as 5, 3, 4, 1. So we see we've taken this one that fixed 1 and changed it into a permutation that fixes 2. So it looks like this is the mapping that we'll want. We're going to want to let phi take h to k. Oh, and let's formally name alpha equals 1, 2. Let alpha be 1, 2. Then let phi take h to k by by phi of, let's call it beta, beta and h, is equal to alpha, beta, alpha inverse. We've just conjugated by alpha. We could call this mapping phi sub alpha if we want. That's what the author has been doing in the book. There's 2 ways you could look at phi sub alpha. We could look at it as a mapping from h to k, and that's what we're doing. But notice that phi sub alpha is really an inner automorphism of S5. That inner automorphism is induced by the element alpha, which is the 2-cycle 1, 2. So it's an inner automorphism of S5, but we're just looking here at the fact that it carries h to k. We're looking at h and k like they were groups on their own. Of course, they're really both subgroups of S5. So we need to prove that phi is an isomorphism from h to k. So let's start by let beta be an element of h, and we want to show that alpha, beta, alpha inverse is indeed an element, a permutation in k. So, well, let's start with then alpha, beta, alpha inverse. And what does it mean to be in k? It means that the permutation fixes 2. So let's see if this permutation fixes 2. That is alpha of beta of alpha inverse of 2. Well, alpha inverse of 2 is the same as alpha of 2. It sends it to 1. So this is equal to alpha of beta of 1. Beta is in h, so beta of 1 is 1, and we have alpha of 1. And alpha is our 2-cycle, 1, 2, so alpha of 1 is equal to 2. Therefore, we can conclude that alpha, beta, alpha inverse is an element of k, and therefore our mapping is well defined. So we go on now to show that alpha, beta, alpha inverse is 1 to 1 and onto, and that it preserves the operation. To show phi is 1 to 1, we assume that phi of beta is equal to phi of gamma for some gamma and beta in H. Well, this implies that alpha beta alpha inverse is equal to alpha gamma alpha inverse. And multiplying on the right-hand side by alpha and the left-hand side by alpha inverse, we get beta is equal to gamma. Therefore, phi is 1 to 1. To show phi is onto, we let sigma be in K. And we have to find an element in H that maps to, under phi, maps to sigma. Well, I just write this. I say phi of what will end up giving me sigma. Well, phi multiplies on the left by alpha inverse, on the left by alpha and on the right by alpha inverse, so it would be phi of alpha inverse sigma alpha. And that gives us sigma. You see for yourself. You multiply on the right by alpha inverse and on the left by alpha, and you get sigma. Or we could say you conjugate by alpha and you get sigma. Now, to show that phi is operation preserving, we have to take phi of, let's say, beta 1, beta 2, and show that we get phi of beta 1, phi of beta 2. Well, phi of beta 1, beta 2 is alpha beta 1, beta 2, alpha inverse. But we can stick in the middle an alpha inverse alpha, which is just the identity, and write this as alpha beta 1 alpha inverse times alpha beta 2 alpha inverse. Notice what I did there. I just put in an alpha inverse alpha, which is the identity. And we got phi of beta 1, phi of beta 2. So the mapping phi is operation preserving, and we have proved that H is indeed isomorphic to K under the isomorphism phi. The next problem, number 24, tells us that alpha is an automorphism of Z20. And it tells us that alpha of 5 is equal to 5. What are the possibilities for alpha of x? In other words, a formula for it. Which ones could it be? Well, look at U20. U20 has 8 numbers in it, and those 8 numbers are those that are relatively prime to 20. So we know that looking at these as elements of Z20, that they are precisely the generators of the group. So these numbers here are the generators of Z20. So any mapping, let's say phi sub I, that maps Z20 to Z20 by phi sub I of x equals Ix is an automorphism of Z20. Now, for those of you who might not have gotten that from what we've been doing in class the last couple class periods, let me just review. Let's just look at, take phi 3. Phi 3 of x. Well, you know that 1 then maps to 3. That's what it means, phi 3. It takes the generator 1 to the generator 3. Well, then it's going to take 1 plus 1 to 3 plus 3, because we are preserving the operation. It'll take 2 plus 1 to 6 plus 3, or 9. It'll take 4 to 9 plus 3, which is 12. And it'll take 5 to 15. In general, it will take k to 3k, right? 3 plus itself, k times. This is so that this is forced on us by the fact that phi 3 must preserve the operation. So all we have to do at this point is just check the different mappings, what they do to 5. So we know that, of course, phi1 of 5 will be equal to 5, because it's the identity map. Phi3 of 5 is 15 mod 20. So that's no good. We only want the ones that map 5 to 5. So if you go through these, you will find that phi9 of 5 is equal to phi13 of 5 is equal to phi17 of 5, and they are all equal to 5. So we have 4 different possibilities for alpha. Alpha could be phi1, phi9, phi13, or phi17. Problem 43. Let G be a group and G be an element of G. If Z is in the center of G, show that the inner automorphism induced by G is the same mapping as the inner automorphism induced by ZG. Well, let's write down those 2 mappings. The inner automorphism induced by G, we denote by phi sub G of X, is equal to Gx G inverse. And the inner automorphism phi sub Zg of X is equal to Zg X Zg inverse. And we want to show that those are the same mappings. In other words, if you want to show 2 mappings or 2 functions are the same, you need to show that for all x in G, phi sub G of X is the same as phi sub Zg of X. So let's take phi sub Zg of X here and write a Zg X, and then I'll change Zg inverse to G inverse Z inverse. You can always do that regardless whether the group is abelian or the elements commute. That's what Zg inverse is. In fact, I'd like to highlight that for students who may, when you take the inverse of something, you always can say in any group that it is G inverse Z inverse. Why? Well, because Zg times G inverse Z inverse is the identity. Inverses are unique. So we can always do that. Now, in this case, we know something about Z. It is in the center of G. So if Z is in the center of G, we know that Z commutes with all elements of G. So I can just bring that Z inverse all the way to the left. And I have Z inverse. XG X inverse, or XG X inverse. And this is for all X in G. So we have proven that phi sub G is the same mapping as phi sub Zg. And we're done. Problem 48. Phi is an isomorphism from G to G prime. You can see I drew a picture there. A is some element in G. And I have drawn a little black circle there for the centralizer of A. We know that that is one of its subgroups. And that phi of the centralizer of A is in G prime. That is the image of the subgroup in G. So the first thing you do in a problem like this, we want to prove that phi of the centralizer is the centralizer of phi of A. So the first thing you do is write down these definitions. These have to be memorized. So let's see, what would be phi of the centralizer of A? Well, that's the image of the centralizer of A. So it's the set of all phi of x, where x was in the centralizer of A. And we could simplify that a little bit. We could say that's the set of all phi of x, where xa was equal to ax in G. Now, what is the centralizer over in G prime? The centralizer of phi of A. Well, by definition, it's the set of all y in G prime that commute with phi of A. So y phi of A is equal to phi of A y. All I've done there is apply the exact definitions. Now I want to show that these two sets are the same. So I'm going to let x be in the first one and show it's in the second one, and then I'll leave the other direction for you. So let's let y be in phi of the centralizer of A. Well, if y is in phi of the centralizer, that's over here, then we should be able to go back in G and say there exists an x in the centralizer of A such that phi of x is equal to y. And we know that x was in the centralizer, so let's note that xa equals ax. That's in G, because x came from the centralizer. Now I want to show that y is in the centralizer of phi of A. So I need to show that y commutes with phi of A. So I just write down y times, or whatever the operation is, y phi of A is equal to, oh, we have our x. Y is phi of x. So it's phi of x, phi of A. Phi is an isomorphism, so it's phi of xa. Now that operation is in G, and x commutes with A. So it's phi of ax. And that is phi of A, phi of x. And phi of x was y. So it is phi of A, y. So we have shown that, here that y times phi of A is phi of A times y. So that means, therefore, y is in the centralizer of phi of A. And now you have to let y be in there and show that it is in the centralizer, in phi of the centralizer of A. So I'll leave the other half for you. Problem 55, phi is an automorphism of D4. And we know that phi sends r to r cubed, and hr it fixes. So we want to determine phi of h and phi of r cubed. One way you could do this is to write out all the automorphisms of D4 and see which one it is. But there's really a much easier way. We want phi of h. So if we notice that h, let's try to write it in terms of r and hr. Well, it's hr times r cubed. So phi of h will be equal to phi of hr, its operation preserving, times phi of r cubed. We weren't given phi of r cubed, but we know that phi of r cubed is the same thing as phi of r cubed. Now we know phi of hr is hr, and phi of r is r cubed. So that's r cubed cubed, r to the 9th, or that is r. So we have HR times R, we get HR squared. So phi of H is equal to HR squared. And we'll use the same method. Oh, we already found phi of R cubed, didn't we? So phi of R cubed is the same thing as phi of R using our properties. Phi of R cubed, and that phi of R was R cubed. When we cube that, we get R to the 9th, but that is mod 4. So we get R. Phi of R cubed is equal to R. All we did was use the operation preserving fact of an automorphism.